we're going to just wrap up what we were talking about last week. We were talking about limits that fail to exist, right? We talked a lot about limits, and we sort of ended up talking about trying to define the kinds of places where limits don't exist. Remember, we said that they don't exist when there's a gap in the function. And that's the reason for that being that the limits from the left and the limits from the right don't agree, right? Ants walking towards the value, in this case, towards the value 0 from the left and the right would anticipate different values, and we can't have that, right? So they don't exist. Limits don't exist where there's a gap. They don't exist where there's unbounded behavior, because there's no point that the ant could ever anticipate stepping on. And then the last case was the one that we hadn't quite resolved yet, right? We were still looking at this one. We were looking at some interesting cases where we took compositions of functions. We took a sine of a function, right? We looked at, if you'll recall, here's the Desmos document we were looking at. If we look at y equals sine theta, well, there's our sine graph, no big surprises. If I graph the function y equals sine of a times x, and a is equal to 1, well, of course, that overlaps with our regular sine graph. But as a gets bigger, that's going to serve to compress the sine function, because now the angles that the sine function is seeing are coming faster, right? If x is equal to pi fourths, we're going to multiply that by a 2. Like in this case right here, we're going to multiply it by a 2. And the sine function is seeing 2 times that x value. The sine doesn't care where the angles you feed it come from. It just responds to the angles that you feed it. So if I put in a pi over 4, the sine function is already going to think that it is going to be seeing a pi over 2. And so it's going to calculate the sine value associated with the pi over 2. And so what that means then is, even though the x value is only at pi over 4, the sine function is seeing a pi over 2, and so it compresses the function, right? We did another, give me thumbs up, thumbs down on that. Does that make sense? Kind of review from last year, okay? And if I make a less than 1, well, then that's going to stretch out the function, right? You probably remember that stuff from last year. Okay, what about if I take the sine of x to a power? Well, if x is being taken to the power of 1, nothing changes. But if x is being taken to the power of like 2, for example, that's going to do some weird things, because now the sine function is seeing whatever the value of x squared is. Well, for one thing, x squared is always positive, right? So it's never going to see the sine of a negative value, okay? The other thing that happens is, as x increases, x squared grows faster than x. And so initially, the sine function, it grows, or it changes pretty slowly, but when you get out here to larger values of x, you start to see that the angles that we're feeding the sine function grow faster and faster, and so the sine function becomes much more busy if I zoom out, right? And then if I make that value even bigger, like, for example, the sine of x cubed, where b is 3, then it even amplifies that whole situation, right? Now we start to grow the angles even faster, and it becomes very busy very fast. Okay? So the last thing we wanted to look at then was this sine of 1 over x. Now think what 1 over x does. Before we do anything, let's maybe just graph the function y equals 1 over x. Well, look what that does. Y equals 1 over x. As x gets really big, unsurprisingly, the function 1 over x approaches 0, right? It makes sense, doesn't it? Because I've got a really large number on the bottom of the fraction and 1 on the top. Well, that makes sense. I mean, like 1/10 compared to 1/1,000,000th. 1/1,000,000th is a lot smaller than 1/10, and 1/quadrillionth is a lot smaller than 1/1,000,000th, and so on. So as x gets bigger and bigger and approaches infinity, 1 over x approaches 0, and so the sine is just going to be getting closer and closer and closer to the sine of 0 as x gets really, really large. But look what happens here when x is less than 1. When x is less than 1, Now the number on the bottom of the fraction gets tiny, and the number on the top stays 1, and so that makes the overall fraction much bigger, right? For example, if x equals 1/1,000,000th, 1 divided by 1/1,000,000th is 1,000,000, right? And so as x approaches 0, the sine function starts to see an increasing number of angles that it's going through, and it's going to start to see the number of angles that it sees speed up and speed up and speed up. And so is it surprising that we're going to see something like that? Right? If I zoom in on this thing, you know, if I zoom out, it's totally predictable. As x gets really big, we approach the sine of 0, which is 0 in either direction. If x gets really big in a positive or negative direction, well, 1 divided by a really big positive or negative number is 0. So that part's not surprising. But the part that's weird is as x gets really small. As x gets really small, the function just gets busier and busier and busier, and it starts to oscillate infinitely. It never it never settles on an answer, does it? In fact, Desmos does a pretty good job of trying to represent what this looks like, but not great. There are going to be some deficiencies here because this is a graphics, a computer graphics situation where it can only graph things that are non-infinite. And so what we see, if we look at maybe a little better graph of that, here's just another representation. Right, there's the sine of 1 over x. We get this infinitely oscillating behavior in the middle. So it doesn't have a limit because the ant could never point to a value that it thinks it anticipates stepping on. And so we would categorize the third type of place where functions don't exist as oscillating behavior, where you get infinitely oscillating behavior. That's a pretty weird one. You don't see that one very much. It's much more common to deal with situations where you've got gaps in the function or unbounded behavior. This is not one that comes up very frequently. Okay, and once again, you get this technology pitfall because the graphing technology can't represent something that oscillates infinitely. You see that a lot with graphing technology. So in summary, then, here's our 3 types of behaviors where limits fail to exist. Okay, breaks in the function. Infinite behavior, asymptotic behavior, increasing or decreasing without bound, in other words, and then oscillating behavior. So before we leave this section and jump into the next part, which is how we evaluate limits analytically, let's look at this bizarre function. Sometimes it's fun to do this in math. Math is really interesting. It presents some puzzling questions that sometimes can't be answered really well. So this is called the Dirichlet function. It's defined this way. It's a piecewise function where the function is assigned a value of 0 if the input is rational and a value of 1 if the input is irrational. That makes sense. So if I input a pi for x, what am I getting back? One. Okay. If I input 9/7, what am I getting back?
0.
Okay. So my question to you then is, can you graph this function? What do you think about that?
I'm going to go with probably no, because since there's an infinite number of rational and irrational numbers, it's just going to be, I guess it could be almost 2 solid lines with points at 1 and 0. But
Yeah, that's good. That's what it's.
that feels a little cheaty.
Yeah, you're right. You can't graph it, and that is what it looks like. Let's just graph this from 0 to 1, for example. So if we're going to graph this from 0 out to 1, well, how many rational numbers are there between 0 and 1? An infinite amount. Okay. So if there are an infinite number of rational numbers between 0 and 1, right? And we can get those numbers arbitrarily close, right? There's no limit to how close we can make those those rational numbers between 0 and 1, what does that graph have to look like? Well, doesn't it have to look like? Yeah, if we're going to look at this on the domain, doesn't it have to look like, has to look like this, right? It has to look like a line segment, and it's going to, I'll do it in a different color. Has to look like that, doesn't it? So there's the red part. What about the green part? If it's irrational. Well, how many irrational numbers are there? Infinite, right? Yeah, and once again, there's no limit to how close those can get together. And so you're going to end up with something, if that's at 1, you're going to end up with something like that, aren't you? Now, do those lines, it looks like a non-function because they line up vertically. It's not. It's not a non-function. It is a function because it doesn't violate the vertical line test, because any value on the red segment is going to have a hole on the green segment, right? But you could never represent those holes in the solid points, and so you really can't draw a meaningful graph of that one, can you? Okay. All right. All kinds of bizarre critters in math like that. So now we're going to move on, and we're going to start talking about evaluating limits analytically. Okay, and this is a probably a more satisfying section than the last one we talked about. Now we're not just going to have to rely on technology or graphs or tables to come up with decimal approximations. We're going to get exact answers, right? Exact answers by evaluating limits analytically. Okay, so first of all, let's just do a quick review. Somebody, help us out here. What does this mean? We can all contribute a little bit. The limit of f of x as x approaches a is L. That's how we would say that, right? What are some key things we need to consider, we need to remember about limits? What does this mean? I've got some function f of x. What's going on here? Somebody who hasn't said anything yet, help me out. Be brave. Talk to me about a limit. You just say the whole thing. Just get us started. We got to remind ourselves what it means to be a limit. It's been a weekend. We got to get back in swing of things here.
It never actually reaches the value.
Okay, for one thing, it never actually reaches the x value, right? We're only approaching an x value of a. As far as the limit is concerned, we never get there, right? And so what is the meaning of the limit L then? What is that as far as, think of it in terms of the ant. If an ant's walking along the two-dimensional graph of this function, what does this mean? As the ant approaches an x value of a, what's the meaning? Go ahead, Lily. Go ahead. You hit it first.
I just said that it gets closer and it stays close and approaches L.
Okay, good. So that's the y value that it's going to keep approaching more and more closely. Good. So that's the y value the ant anticipates stepping on, right? And so we went a little further with that, and we introduced this concept of one-sided limits. So we said that the regular two-sided limit of f of x as x approaches a is equal to L if and only if. Now, remind me real quick from last week, what does this mean? How would we say that, and what does that mean?
As x approaches a from the left.
Good. Okay, so the limit of f of x as x approaches a from the left is L, and what about this one? The limit of f of x as x approaches a from the right is also L. So the two one-sided limits have to agree in order for the two-sided limit to agree. Good. Okay, so what is this limit? The limit of g of x, which is graphed here as x approaches -1. Good. Because that's the value that the ant anticipates stepping on, right? Good. Okay. So some properties of limits here. Now we're going to start jumping into doing some harder problems involving evaluating limits analytically. So first thing is, we'll notice here that this says that the limit of f of x as x approaches c does not depend on the value of f at x equals c. It may happen, however, so sometimes if we're lucky, the limit is precisely f of c. Okay, so in those cases, when, in other words, let's couch this in terms of our calculus ant. If we've got a case where the calculus ant anticipates stepping where he actually would step, if he took that final little itty bitty ant step, then it's very easy to calculate the limit, right? Because the place he anticipates stepping ends up just being the value of function at c, right? When that happens, evaluating limits analytically is extremely simple. We just end up using direct substitution, right? For example, if we go back to this previous picture here, right? So what is the limit of g of x as x approaches positive 1? And just assume it's a convenient value. As x approaches 1, what value does it seem to be approaching? There's 1. Let's just pretend it's that nice convenient value. So 4, everybody agree? Well, what is, in this case, what is g of 1? Four. That worked out great, didn't it? Even if we didn't have the graph right in front of us, this is a place where we could have easily just plugged 4 into our function to find out what the limit was going to be, right? Because the ant actually ends up stepping where he anticipates stepping. Now, we don't have that luxury when we're taking this limit down here, do we? The limit of g of x as x approaches negative 1, we can see on the graph that it's 3, but what is the value of g of negative 1? Let me jump in there quickly. We don't want to waste time. What is g of negative 1? 4, yeah, right? Because that's where the ant would actually stand if he actually did take that last step. He would jump up to that point right there, wouldn't he? Right? So this limit down here this limit as x approaches negative 1, we could not evaluate this. If we didn't have a graph, we could not evaluate this directly, because if we tried to just evaluate the function at negative 1, we're getting a different answer than we get with the limit. But because the ant actually steps on this point right here, even if we didn't have the graph, we could evaluate the limit of g of x as x approaches 1 by just directly substituting 1 into the function, right? So when we're able to do that, when direct substitution works, if the limit ends up predicting where the ant will actually step, taking a limit is as easy as can be. You just plug the value into the function, and that's the answer, okay? Now, such well-behaved functions, and we literally use that terminology in math, the reason they're well-behaved is because they're continuous at c. Now, we haven't really talked about continuity yet, so we're going to come back later in the very near future, and we'll shed some additional light on this, and this will make even more sense. You'll be able to look at it from a different context, which will help you to understand it even better. So some basics then, and let's just look at the graphs of these for a second. What about number 1? The limit of b as x approaches c. So what is the function here, first of all, that the ant is walking along? F of x equals what? B. Yeah, right. We're taking the limit of f of x. And so we're just looking at the graph. We have f of x equals b. Well, that's a pretty easy one to graph, isn't it? If I graph the function f of x equals b, isn't that just the graph right there? Oops, sorry, that's not the graph. What's the graph? What am I doing? What's the graph of f of x equals b? What's that going to look like if y equals a constant, or f of x equals a constant?
Some horizontal line.
Some horizontal line, and we don't know what b. I just randomly picked a value of b. It could be positive, it could be negative. But the point is, if this is the line, f of x equals b, regardless of what x value you pick, the value of the function is always going to be b, isn't it? So we could use direct evaluation here, and we know that regardless of what value we're picking for x, the answer is always going to end up by direct substitution, or direct evaluation is always going to end up being b. Easy. Okay, what about this one? Now we've got the limit of the function is, whoops, different color. Now we've got the function f of x equals x. Well, that's just a diagonal line through the origin with a slope of 1, isn't it? Y equals x. And so now if x approaches a value of c, well, if my x coordinate is c, what's my y coordinate going to be? Guaranteed. It's going to be c, isn't it, right? And so now we know that regardless of what x value we pick, as x approaches c, the limit is going to be c also. The y value is going to be c. So there's another real basic limit that was always going to be true. And then I'm not going to go into a proof of this one, but we could do the same thing with a power of x, right? And here's another way we could describe this. The function x to the n is going to be well behaved, right? If it's an even power of x, it's going to have even symmetry. And it's going to look something like this. You know, if it's a parabola, it looks like that. If it's a higher even power of x, like x to the 4th or x to the 6th, it's just going to square off the bottom a little bit more. But I'm always going to get this even function that's got folding symmetry about the y-axis. And the important thing is that the ant will always end up stepping where he anticipates stepping as he approaches any given x value. So this is another one that we can just evaluate using direct substitution. If it's an odd function, same thing is true. If it's an odd function, it's just going to have rotational symmetry about the origin. But once again, it's a wave function where the ant will always step where he anticipates stepping in the limit. And so we can use direct substitution and just plug the value of c into the function to see where he thinks he's going to step. Okay? Give me thumbs up, thumbs down, thumbs sideways. How are we doing on that? Okay? Okay? Okay, I mean, it's not maybe 100% clear, but it will be. I promise you it will be. What happened there? Let's see. I don't know what was supposed to be there. I guess nothing. I don't know. Okay. I'm going to do one. Let's do one more example just to make sure everybody's clear with this. I want to make a graph. What do you think? Anybody tell me the answer? Just type it in the chat. How about?
3.
Yeah, it's 3. It's 3. How do we know that? The answer is 3. Well, the reason we know that is because I can use direct evaluation. If I were to graph this function, it just looks like this, doesn't it? If I were to graph it. If I go out to x equals 9, clear out here to x equals 9, what's the value of that function at 9? This is f of x equals the square root of x. When x is 9, What's the value of the function? F of 9 equals the square root of 9, which is 3. Okay, so that's where the ant actually would step if he went to x equals 9. But wouldn't you agree that if the ant were to approach 9 from either direction, he's going to anticipate stepping there, isn't he? And what's the easiest way to answer the question, where does the ant anticipate stepping in this case? Is to calculate where he would step. Because this is a function where that behavior exists. He would step where he anticipates stepping. So we can take a shortcut and just ask ourselves, okay, well, the limit, in this case, the limit of f of x as x approaches 9 is exactly equal to f of 9 because he's going to step where he thinks he's going to step. That's easy. That's just 3. Okay? All right, a couple other... I'm going to come back to this. I'm going to come back to this stuff. Yeah, we'll come back to this. I think this interrupts our train of thought right now. We'll come back to this in a little bit. What about this guy? Okay, polynomials. We've dealt with polynomials for years and years now, at least 2 years, right? And we know that polynomials can get complicated looking, but what's the domain of a polynomial, any polynomial? Here's an example of a polynomial, right?
All reals.
It's going to be all reals, yeah. Right? And we know that polynomials are continuous everywhere, meaning, we've talked about this a little bit in the past, meaning that when we draw a polynomial, we never have to pick our pen off the board, right? We can always, in other words, what that tells us is that polynomials are well-behaved functions. They're functions where, if we're taking a limit, the ant would always end up stepping for any value of x where he anticipates stepping as he approaches that value, right? So for that reason, polynomials are super easy to deal with when we're taking limits. All we have to do is evaluate them directly, right? I'm just going to plug 2 in for x, and I'm just going to end up getting 4 times 2 squared plus 3 gives me 16 plus 3 is 19, piece of cake. Okay, we don't have to, it's not complicated at all. I'm just going to plug in, I'm going to substitute directly, piece of cake. What about the limits of rational functions? Okay, if p is a polynomial and q is a polynomial, then that's how we define a rational function. A rational function is a ratio of polynomials, right? Okay, well, what do we know about rational functions? Going back, I know we talked a lot about this in Algebra 2. You probably talked a lot about it last year, too. What's the domain of a rational function? Like, let's take this one, for example, right here. Here's a rational function. I've got a polynomial on the top and a polynomial on the bottom. Okay, what's my domain for this function? What's the only x value we can't have? -1. There you go. So x cannot equal -1. Okay, so at -1, we're going to get something weird happening, right? -1, we're going to get something weird happening. But every place else on this function, it's going to be fine, right? So at all the other places, we could just evaluate directly. But we can't do that at -1 because the function's not defined there, right? But every place else, we'd be okay to just use direct evaluation. Okay, so that's the point that we're, that's the point that we're trying to make here. Okay. Okay. You can, in other words, let me state that one more time. You can apply direct evaluation when taking the limit of a rational function every place except where the denominator is equal to 0, where the rational function is undefined. So once again, those are easy to deal with. Oh, is that us already? It is. Okay. Well, we took a little bit of time up with the Math Excel stuff. So I'm going to go ahead and not going to give you an assignment over this yet. We'll finish this up on Wednesday, and then I'll give you an assignment over this. Okay, I might give you just like a 1 or 2 problem little e-ticket, really simple stuff, but we won't get another assignment until Wednesday. And I'll put it on Math Excel, so that's where you'll find it. Okay, I better let you go. Alrighty. Have a good day. Bye.